Okay, let's move on to part 2 now of this lecture. So at this point you're saying, oof, you covered a lot of material on the last lecture. Well, we did. Now we've covered how electron and hole concentrations change with thermal generation, doping, recombination, optical generation. We even talked about how you can get light emission from a semiconductor. And at this point, to motivate you, I can say we have one more major topic we have to do before we can start learning devices, and that is current flow. And so today we're going to learn about two types of current flow. The first type of current flow is drift current, which is driven by an electric field. So if I have a block of semiconductor here, in this case it's silicon, and this could be p-type dope n-type doped here, so I have phosphorus atoms here, and if you notice in this case the number of electrons I have is more than the number of holes because there's some phosphorus atoms for n-type doping. Just as an example, and I put positive here and negative here for my voltage, then my E field is in this direction, then of course I would expect my electrons, which are negatively charged, to travel towards the positive end of the E field, and my holes to move along with the E field direction towards the negative end of the voltage or E field. And so this is drift current. It's very simple, and you're very familiar with this because this is how you've understood electronics for a long time. Now, what's interesting about semiconductor devices is that drift current's important, but equally and more important for many devices is diffusion current, which has nothing to do with E field. It has to do with diffusion, which is entropy driven, meaning that something that is ordered wants to move to something that is disordered. And so for a silicon system, the example is that basically, let's say I start off with a bunch of electrons all on this side. And let's call this ordered because I'm trying to, let's say I'm trying to move all the electrons to one side and make them nice and orderly over here and clear them out from over here. Well, entropy says, nope, they should be spread out. And so what's going to happen is these are going to try to move from high concentration here to low concentration where the concentration is even everywhere to spread everything out. And so, a good example would be all of you in here. So if I had you all, well, you're not in here, you're in a classroom, but if you're in a classroom and I had everyone line up against the wall and I left the room, over time you would diffuse randomly around the room. So even you are subject to entropy over time. So let's look at drift current in greater detail here. And so the first thing I want to focus on over here is the drift current equation here. And so how we calculate drift current density meaning amps per unit area, and in this course we use CGS units, centimeter gram second, so it's centimeters squared. We can calculate current density as follows. Now, if I have current, right, amps are equal to coulombs per second, right? And so I need to have a coulomb. Well, how am I going to get a coulomb? Well, in my equation, here is Q, which is charge of an electron, in coulombs. This gives me my coulombs in terms of coulombs per second. The next thing I need to know is how easy is it to move this charge through the semiconductor. And this term, mu sub n, is called mobility. Okay, so mu sub n here means mobility for electrons, hence the sub n. And the units are centimeters per second divided by volts per centimeter. And so this should make a lot of sense. If you look at mobility, it basically says how fast can you move, velocity in centimeters per second, divided by how much force or E field did you need to apply to move it. How fast divided by how much E field. If you can move really fast with just a little bit of E field, that would be a large number over a small number, which gives me a large number here, which gives me a high mobility. So that should make complete sense to you. If not, please go through it again. So if I have Q, I've got mobility. The next thing I need to know is what's my concentration? Because if I only have a few electrons, I'm not going to have much current flow, right? So this gives me the number of electrons I have. And the last thing I need to know is, well, how much electric field? Because if I have more electric field, then I'm going to get more current flow. I have a stronger driving force. And so if you look at the units here, you multiply these all out, what you'll end up with is all of this stuff will cancel out, and you'll end up with coulombs per second okay, which is amps. And if you cancel out the centimeters, all the centimeters, you end up still with a 1 over centimeter squared, which turns us into current density. So a little bit more about mobility. Mobility is it's never perfect. It's reduced by scattering from ionized dopants. It's reduced as the temperature increases, as the silicon atoms are vibrating back and forth. They can get in the way of electrons trying to move forward. And as you increase concentrations, mobility goes down. So you can find electrons, as they're trying to move in this direction, start bumping into each other. And so a good analogy for that is if you look at a highway, as you increase the number of cars on the road, at some point their mobility decreases and you get a traffic jam because things can no longer move forward at an orderly fashion. They're in a threat of running into each other. And in the semiconductor system, they start running into each other just like you actually see sometimes on a crowded highway. So that's how we calculate our drift current, which is caused by electric field. Let's look at how this is drawn on a band diagram, and this is critically important. And so if I have a band diagram, and again, this we said we'll have N-type material, so my Fermi level is closer to the conduction band. I've got more electrons than holes. When I apply electric field in this direction, for the positive side, I push the bands down. For the negative side, I push the bands up. And now I have a sloped band, as you can see here. My E field is uniform. It is constant across here, and so my slopes of my line should be constant. That's important to remember as well. And so the strength of the E field at any point is shown by the slope of this line. Now, continuing along, how I like to remember this in terms of which way the carriers flow is something I call the soda pop analogy. So in this course, if you're ever confused about this, remember that you can think of the electrons as being like water. So if I poured water onto this conduction band, it of course would flow downhill in this direction. And that makes sense because this is positive, and so negative charge should go in this direction. And if you see how I bent the bands, positive pulls the bands down. The water, or the electrons, flows this way. The beauty of the soda pop analogy is that a hole is the absence of an electron. Well, what would be the absence of water? Well, in soda pop, it would be a bubble in the water, right? And the beauty of that analogy is that if bubbles are the absence of water and holes are the absence of electrons, in water, bubbles float up, right? And so look at the band diagram. If it's tilted this way, the bubbles float up to their minimum energy against the valence band, and then they float up and they travel in this direction, just like you would expect a bubble to do. And furthermore, here's the negative side, pushes the bands up. Well, we expect positive charge to go towards the negative end. So again, anytime we're doing band diagrams in this course and we're talking about drift current, try to remember this soda pop analogy where the electrons are the water and the holes are the bubbles in the water. And always remember this, you need to get really good with this. When I say positive voltage, you should be instantly thinking bands get pushed down. If I say negative voltage, you should be instantly thinking the bands get pushed up. And remember, as I'm applying voltage, I multiply it times the charge of electron, and that gives me electron volts, which is energy. This is an energy scale, and so you're turning that voltage times the charge of an electron, which shifts the energy up, which you would expect. So let's do a quick calculation example for drift current. Let's assume we have a silicon bar that is 0.1 centimeters long and 100 micrometers squared in cross-sectional area. Let's dope it 10 to the 17th with phosphorus and ask ourselves, what is the current with 10 volts applied? I'll just take the equation we had on the previous slide. I will substitute in charge of an electron for Q. The mobility I have to look up on a table, so here's a chart of mobility versus doping level. I said I was at 10 to the 17th, so 10 to the 17th. I'm looking at electron mobility, so mu sub n. I trace it over here, and I see that I'm about at, since this is a log scale, I'm at about 700 centimeters per second per volt centimeter. Next thing I need is my concentration of electrons, which is 10 to the 17th. I gave you that to start. I need to know my E field, which I said I have 10 volts over 0.1 centimeters, so 10 volts divided by 0.1 centimeters. Again, units of centimeters, 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 so put the length in centimeters. And lastly, because I want current, not current density, I need to multiply by the area. 100 micrometers squared, cross-sectional area is 10 to the minus 6 centimeters squared. I finish the calculation and I get 1.1 milliamps. You could also do it this way. You could directly calculate the conductivity of the silicon from Q, mu sub n, and the electron concentration, which is the inverse of resistivity. And then you could just insert this into rho L over A using the dimensions I have, then insert resistance into I equals V over R. So you could do it that way as well. Let's move on to our second type of current, which in most semiconductor devices is actually more important than drift current. And the second type of current is diffusion current. So again, diffusion relies on random motion, which means that you need some temperature. So if I have, a bunch of things sitting on a table, if I put no energy into the system, they will just sit there. But if I put energy in the system, they can start to move around and vibrate. So we're assuming that we're at 300 K or something like that, room temperature. And what this does then is these things are moving around in all directions. Eventually they will move around and spread out to a more random and evenly spread distribution. A great analogy is if I have a vial of water here and I started with dye at the bottom, the dye over time will diffuse from a high concentration at the bottom up to the point where it's trying to equilibrate its concentration all the way through the water. So you see that same experiment shown here. Now, the diffusion current can be calculated by the diffusion current equation, and this tells you how this all happens. And so it's really beautiful in terms of how this works. So the first thing I have, if I have current, and in this case again it's current density in terms of per centimeter squared, amps per centimeter squared, is again I've got to have a coulomb, right? If I'm going to have coulombs per second to give me amps, I better have Q up here. So this is my charge of an electron in coulombs. The next thing I have is not mobility, but I have diffusion coefficient d sub n. Let's look at d sub n here. So what is d sub n? Look, how's it calculated? Well, it is calculated by mu sub n, which is mobility, times kt over q. Well, mu sub n we talked about on the previous slide, that's mobility. So how easy is it to move a carrier through a semiconductor with a voltage or with an E field applied? So why do we need mu sub n? Because we're saying we don't need voltage to move here. Well, the reason why you need mu sub n is that we can turn temperature by multiplying it by Boltzmann's constant and dividing by the charge of an electron to basically get units of volts. And so this is what we call, KT over Q is called thermal voltage. It is critically important. It comes up again and again in this course. And so be able to recognize that KT over Q is thermal voltage and that it is the driving force that when I multiply it by mobility gives me how easily things will diffuse. And so for a given temperature and a given mobility, I will have a given diffusion coefficient which will tell me how easy it is to diffuse. And if I have higher mobility, easier to diffuse. If I have higher temperature, I've got a stronger driving force for this and I get a higher diffusion coefficient. So I've got coulombs. I've got how easy is it to move by diffusion, which is diffusion coefficient. The last thing I need to have, and which you must always have, is a concentration gradient. Again, I started with a high concentration here and it wants to spread out. And so if I must have a concentration gradient, and that's calculated by basically what is the difference in concentration over distance. And so obviously here I have a change in concentration as I move distance x here. And so this would be a positive and real number here. You multiply the units out, you have coulombs out front, you have d sub n, which has units of centimeters squared per second. If you calculate this out and do all the units, you put everything in here, so you get centimeters squared per second. And then if I take the derivative of 1 over cubic centimeters, it becomes 1 over centimeters to the third, becomes 1 over centimeters to the fourth. Multiply everything out, you'll see you'll indeed get amps per centimeter squared, which is current density. And again, when you get to 300 K, at the end of this, it moves out to a more evenly spread concentration. Remember, that does not mean that the electrons then just stop moving. At 300 K, the silicon atoms are vibrating back and forth as phonon energies. So that's a phonon, which is vibration of the silicon. And the electrons are also moving around. And they're moving around until they find a hole to recombine with. And as I mentioned, in some cases, diffusion is more important. In fact, when we forward bias a diode next week, we will see that current is not driven by E field, which is drift, but it's driven by diffusion, which is unexpected because you use voltage to turn on the diode. Let's look at some example cases for diffusion current. Let's assume I have a plot here of electron concentration versus distance, and at t equals 0 I have this electron concentration here. So I have this nice little high concentration of electrons concentrated over a very short distance x. I would expect as I go to T1 and to T2 that eventually this concentration will want to spread out to an even concentration over time. And you can see that you go to T1, T2, it's spreading out. So the question is, at what point in time will the electrons move fastest? Would it be T1 or T2? Well, if we went back to our diffusion current equation, you would find that the diffusion current is a maximum when the concentration gradient is highest. In this case, I've got a huge concentration gradient. I've got high concentration here, 0 here over a short distance. And so the movement and spreading is fast. In this case, I've got a lower concentration change over a larger distance, so dN dx in this case would be less. And so you would see slower movement here. So the fastest spreading happens right after t equals 0, and then over time it spreads out more and more. A nice analogy would be if I have a column of water here and you just magically created a column of water and you just basically then let it go, it would very quickly spread out, and as the water got thinner and thinner, it would spread out into a bigger puddle, but the spreading rate would decrease over time. And that's just an analogy. The physics, you can't calculate with the same equations, but it's just an analogy for you. Okay, so let's look at a figure here of what diffusion looks like in a more practical case for a semiconductor. Let's assume that I'm plotting concentration versus distance, and I'm injecting an excess of delta P right here at x equals 0 continuously. And so right here at x equals 0, I basically am creating delta P excess, and P naught is my background concentration. So here's my silicon, which has a normal thermally generated hole concentration of P naught. And right here at x equals 0, I also put on top of P naught this delta P here, which is an excess. And so let's look at what happens. Well, if I create an excess and I've got low concentration out here, then I should expect to see current flow from high concentration to low concentration, which is diffusion current. And so how do we calculate this? Well, or at least the profile here. What you'll see with the profile, and we'll calculate this in a second, is that the concentration decreases with distance. In fact, it decreases exponentially with distance, and I'll calculate that in a second. What's happening is that as I create an excess here, and these excess holes are moving in this direction, they're also recombining with electrons. So the excess starts dying off, because if I have an excess, I'm going to have even more recombination. It's going to recombine faster. And so even though they're trying to move in this direction, they're also dying off and going back down to the normal thermally generated carrier concentration as they're recombining. Now, the average distance they will go before they recombine is the diffusion length. We talked about that last time. I can now calculate diffusion length as the square root of diffusion coefficient and lifetime, and that should make complete sense to you. If diffusion length is sort of the statistical average for how far can I go before I recombine, then what I need to know are two things. One, how long do I have to live? So if I want to go somewhere, how long do I have to get there? So that's my lifetime. And then the second thing I need to know is, well, how well am I able to move to get there? And that's diffusion coefficient. So if I have a high diffusion coefficient, I can go further if this increases. And if my lifetime increases, I can get further as well. So how do I basically get this profile here? Well, what we need to do is start with the general diffusion equation, which is a continuous second-order differential equation. You haven't had differential equations, but I can teach you. You'll learn about them in some of your courses, and they're pretty easy to understand. Basically, differential equations are equations which give you general behavior for some kind of system. So if I look at, for example, at a pendulum swinging, or a harmonic or an oscillator, or vibration of a string, all of those have a general equation which tell you how that thing will behave generally, but not with any bounding conditions. So if I had a vibrating string, I could apply a differential equation and put the boundary conditions being the length of the string, and then figure out a particular frequency at which it vibrates, right? So if you have a shorter string, it vibrates at higher frequencies. And so that would be how you apply a differential equation to a mechanics problem. Well, in this course, we'll take a second-order differential equation here. And because we're looking at this in steady state, meaning we're not changing things with time, we just keep injecting delta P and we keep doing that forever, we're not changing that with time. There is no time dependence, so I'll get rid of this term. And I'm left with these two equal to 0 then. I'll move one of these terms over to the other side, and that gets rid of the negative sign, and I have this term here equal to the remainder here. I'll put dp over to the other side, so I'm bringing dp over to the other side. It's there. So I've got this differential equation for which I'm looking for a specific solution for this case. And so if I look for a function which I could put in here where the second derivative of the function is equal to the first derivative of the function divided by dp tau p, if the second derivative of the function is equal to just the function divided by dp and tau p, then what kind of function could that be? Well, the answer is that it should be a exponential, okay? And so anytime you take an exponential, the derivative of it, you basically get the same equation back, and some of the stuff falls out of the equation. And so this is a general solution here which satisfies this differential equation. And then we apply boundary conditions. We know that C1 must be equal to 0. So if you look at this equation, and you're like, well, where do my dp and my tau p come from real quick? Well, look up here, I have got 1 over LP. So if I take the derivative of this exponential, my 1 over LP comes out, right? In fact, if I take the second derivative, I should have 1 over LP squared. Well, if LP is square root of dp tau p, then LP squared is just dp tau p, and that's where my dp tau p shows up from. So let's come back to our boundary conditions. So I know for this system I can apply some boundary conditions. The first one I can say is that C1 must equal 0. And that's pretty easy to figure out why, because if C1 does not equal 0, this says as I go in further distance x here, that my concentration goes to infinity. And we know it doesn't do that. We know that if you inject holes further out into the semiconductor, the concentration doesn't go up to infinity. So I can assume that C1 equals 0. The next thing I can do is I can say, well, what's C2? Well, I have a boundary condition here. I said that at x equals 0, my excess was delta p, right? I started that as a defining bounding condition for this differential equation setup. And so at x equals 0, my concentration has to be equal to delta p. So if I'm at x equals 0 then, okay, this goes to 1. So if this is 1 and my excess is delta p, then my excess must be equal to C2, and C2 must equal delta P. So I put that in there, and I end up with the following, where if I solve for delta P, I also have a constant at the background which I add, which is my background concentration. I have my concentration profile, P sub x, is equal to delta P, the excess at the interface here. Then it exponentially decreases with distance, as this differential equation predicted, and as you can see here, because of recombination of those holes. And then the minimum level it gets down to is the background concentration P naught. And so this is, and I could basically also just show this as delta P, where this whole term here is just the capital delta P here. So I've given you a first example, which will show up in this course again and again, of how you can take a differential equation, which predicts general behavior for some kind of system, simplify it down, apply boundary conditions, and come up with a specific solution which gives you a formula to predict behavior in your specific system that you're looking at. Okay, well that finishes it for drift and diffusion current. Finish the review, and I look forward to working with you on this in class this week.